Thursday, we started talking about what forces are. We gave a generalized kind of, these are all of them. These are kind of, well, not all of them, but these are a whole bunch of them that we're going to be talking about, some of them more than others. We talked about the big four. We gave a definition for what a force is, where F equals ma comes from. And then I introduced you guys the concept of free body diagrams, analyzing what forces act on an object and how we can diagram them using this. I think, there was one more that we hadn't. The bell was about to go, or the bell went rather, and we were in the process of talking about these ones at the end here. A plane flies at a constant velocity. So this is what the diagram looked like, and I was about to ask that if a plane is flying at constant velocity, what needs to be true about all these forces on here? They're all balanced, which means these two are equal, and these two have to be equal. The drag from the air and the applied force from the engines needs to be equal, as well as the lift and gravity. Excuse me. And then the last one that we were going to draw, or that you guys had drawn, we hadn't gone over yet. A car is coasting to the right and slowing down. We wanted to diagram the forces acting on the car. So, I mean, I'm using blocks and balls for most of these things, but a car is easy to draw. It's just a block on wheels. What forces did you guys have acting on that car? Gravity, always a safe bet. Friction's acting which way? Well, which way is the car moving? Oh, to the right. So friction would be which way? There would be friction to the left. You could call it friction. Friction would be part of it. It would be a combination of friction and drag on the car, depending on how fast that car is moving. Drag would be pretty small. It largely would be friction. Almost certainly friction within the bearings of the wheels, yeah. And then there was one more force acting on the car because it's not falling into the ground. Normal force. The car is sitting on a surface, therefore there has to be some upward force on it. It's not falling into the surface. Like quicksand would be an interesting one to draw here, because quicksand would still kind of have a normal force, but that normal force would be smaller than gravity, because, I don't know, growing up I always thought quicksand was going to be a bigger part of my life than it is, but it's sort of semi-solid, holds you up well enough until it liquefies and then you start to sink. But you're not in free fall. Yeah. There is a word in there that suggests that there is no applied force. Nope. There's a word in there that suggests there is no applied force. Coasting. That's the is I gotcha. Or you push, if you're driving a standard, you push the clutch in, you put the car in neutral. Have you ever driven a car? Okay, I don't know. I don't know. Just because you don't have a driver's license doesn't mean you've never driven a car before. Varied, see? Varied, I would not have assumed that. Very different though. Yeah, coasting, that word coasting, again, all of this, lots of this is about analyzing the language that's there. That word coasting means if the engine is on, it's not impacting the car at all. Either the car is in neutral, you've pushed the clutch in, or the car could be off and it's just, you were driving. I had an idiot buddy who would do this to people. You're driving the car and he just reach over really quick and turn the key off. Just to be a jerk, which isn't the word we use, but that's the word I'll use here. He would do that to people all the time, to the point where people stop driving in places. But at that point, you would be then coasting. Ass. But he was a good friend of mine. So those are free body diagrams. For dynamics, those are non-optional. Every problem that we're going to do here, and moving forward, you will have to start including these free body diagrams. So let's talk about Newton's laws. Newton had 3 of them. Does anyone know them? I mean, I kind of start this one here. Newton's first law: an object in motion will blank, and an object at rest will blank unless blank. Here today? No. We have blanks to fill in, and F net equals ma doesn't fit here. F net equals ma, I think, is actually law number 2. Where's law number 2? That's law number 2. This box right here is F net equals ma. Alexis. Will stay in motion, and an object at rest will stay at rest unless acted upon by an. Now, there's a few words that could fit in here. In the original formulation that I heard said an outside force, but to keep it with the language that we've been using so far, I'm going to say, or the word I'm going to use is going to be unless acted upon by an unbalanced force. So that's a classic. It's one of those things, like, if people are going to start to try and sound physicsy in pop culture, this is something they'll try and throw down. For example, my wife and I have been binging Modern Family, and they try and make Alex sound really smart. And so they'll get her to throw out things, and she'll say them kind of quickly. And your average person's going to think that she sounds really smart because she's at Caltech and she's doing these things. And she said what she said, and I was like, wait a second, that's high school physics they just tried to shoehorn in there. I'm like, that's poor writing. Like, it's not. But for a person who has never taken a physics course, this can sound really smart. And I mean, for Newton to come up with this, like, no one had formulated these laws of physics the way Newton had. And so, I mean, it's not dumb, but it's certainly not earth-shattering at this point. This word unbalanced, Hirde already used language that we're going to use around these unbalanced forces. An unbalanced force we also call a net force. So an object in motion will stay in motion, an object at rest will stay at rest unless acted upon by a net force. Sometimes is how this is referenced. This word net has a mathematical implication here. Does anyone know? Or I mean, even in the context of like taxation, this word net means kind of the same thing. Does anyone know what that word net implies? Like, so if you're taking accounting, you've got gross income and you've got your net income. Gross income is everything you've made. Net income is after deductions. So it's the total minus whatever your deductions are. So a net force, yeah. In a very specific example, that would be true. Generally, the way I'm going to say it, a net force is a sum of all the forces. Sum of all forces not equal to, so the equal sign with the slash through it, not equal to 0. If you add up all the forces and they're not equal to 0, you have a net force, whatever that is. In some cases, it's going to be the difference between applied and friction. In other places, it'll be the difference between gravity and tension, or elastic force and gravity, or like it could be any sum. But for there to be a net force, you're going to have a non-zero sum of all the forces. Do we have notation for sum in math? Which I'm going to put, where am I going to put it? Because I didn't say this last time. I'll put it down here. Does anyone know what the sum notation is in math? Capital Greek letter sigma. Nobody? It's a spiky looking E. Sometimes they call that symbol summation notation. And so the way that we write this is that there is a net force. We say that the sum of all of the forces or that spiky E, the sum of the forces is not equal to 0. This is also referred to as the law of inertia. Inertia is, which we have talked about a little bit in the first chapter. I'll define it here again. Inertia is the tendency. Red pen sucks. Let's go to a purple pen. This also sucks. That's sad. Let's go to this color. The tendency for an object to maintain its motion. So if things have a lot of inertia, it takes a lot to change their motion, whatever that is. If they're not moving, getting them to start moving takes a lot of work. Or if they are moving, bringing them to a stop takes a lot of work. So for example, let's talk about it here. Inertia is the tendency for an object to maintain its motion. It's dependent on two things. Let's go like this. Does anyone want to take a guess at what inertia depends upon? Mass is 1. Not friction. Friction works to stop things. So it is one of these forces. The tendency for an object to maintain its motion requires properties of the object. So if an object is very, very heavy, it has the potential for a lot more inertia. For example, if my daughter is walking at you, she's 3, or if I am walking at you, which of the two of us is going to be easier for you to stop? Probably my daughter, who's barely 40 pounds, versus me, coming in at around a little over 220. I'm going to be way more difficult for you to stop than she is. That's only part of it, though. You don't want to take a guess at the other half. There's one other property that's connected to inertia. Yes, but simplify that down. Not just kinetic energy is the combination of mass and velocity, yeah. I mean, we can talk about my daughter again, or my son, because he does this all the time. My son walking at you, he's 2, easy to stop. My son running at you is a little bit more daunting because he does this thing lately where he'll run at you and then come at you with his head. So like I'll walk in and he's right at the perfect height to really get damaged by this. He will run at you and then lean into you like a football player and just come at you with the front of his skull. It hurts a fair bit. He's being a little dude. There's a lot behind him. But I mean, even if you think about a football player, like let's extend this. You have a 200-pound wide receiver running at you, or a 300-pound lineman running at you. Mass is going to be involved there. But let's talk about the 300-pound lineman. So Fuj, PE teacher here, if he was walking at you versus he was running at you, which would be more daunting? The running. 300-pound man running at you is going to be a lot more difficult to stop. So inertia is a combination of these two things. You notice inertia in 3 places, really, when you're moving, and that's when you try to change this. Wherever you try to alter the motion of an object, you really start to notice its inertia. So where do you change? What does changing velocity look like? Speeding up is 1. Slowing down is another. And there's one more. Stopping. Nope, stopping is slowing down. There's one other way to change velocity. Velocity is a vector. It's made up of, it has a magnitude and a. So changing a direction means you're doing what? Turning. Which we did kind of talk about already in the first chapter. Like when you're turning, the car turns around you, your body wants to continue in a straight line, which is why it feels like you're getting squished up against the side of the car. That's just the car trying to bring you back along its path. But these are the big three: speeding up, slowing down, and turning. And sometimes inertia can really surprise you. Like the classic example is like you're pushing a car. The car is moving, or if the car is it's rolling at you slowly. The number of people, it's been, so I'll say it this way. There is a surprising number of people that I have seen, I've witnessed personally be like, oh, the car is rolling, I'm just going to stop the thing. Even if it's rolling very, very slowly, actually leaning into the thing and catching it or stopping it doesn't happen easily. Like there's a lot of mass there. Even for a slow moving object, there's a lot of mass there. Or we can bring it up. We can talk about it the other way. If the mass is very, very small and you've got an object moving very, very quickly, it's going to hurt to bring that thing to a stop, which is why how much it hurts hitting you is another example of how much inertia it has. The example I gave you, I think it was a couple days ago, with my buddies and I trying to catch golf balls. Like we had one buddy at the far end of the field and he was driving golf balls at us and we were like, yeah, we're going to catch these things. Idiots. It hurt. I took one off the thigh. It dropped me. I was done. But these, and it's like my cousin and his buddies would shoot air rifles at each other, just to do that kind of thing. These guys are stupid. Small objects moving very quickly, large objects moving very slowly, still have both cases have tons of inertia. So this is another way to think of Newton's first law is that if there is no net force on an object, then it will stay at constant velocity. We talked about it Thursday. I introduced you to this concept of F net equals ma, the idea that for an object to accelerate, there has to be some force acting on it, some unbalanced force acting on it. So this is the same kind of idea. If there is no net force, so if we bring this in here, so I add F net now equals ma. If this is 0, the only way for this to be 0 is if the acceleration is equal to 0, because it's not possible to have an object whose mass is 0. The only quote-unquote object that we are aware of in the universe that has a 0 mass is a photon. This is why you don't feel light hitting you. Because it does, and it bounces off you. That's how we see other people, but it has no impact upon you. So there is no impact. If this is 0, that means this has to equal 0. And if acceleration is 0, there's kind of two ways you can have acceleration equal to 0. You could have a moving object that is maintaining its velocity, or you could have a non-moving object. This is the other way it often gets quoted. If it's not moving, it has a constant velocity of 0, as well as an acceleration of 0. So imagine, if you will, a book sitting on a table. There is a force of gravity pulling down on the book, but there is also a supporting normal force pushing up on the book. It's the same kind of free body diagrams you guys drew yesterday. I've got my table. I've got my book. We have Fg down. We have Fn up. If we just analyze this, let's call upwards positive, because up usually is. If the book is not moving, if it rests, in this case, the normal force Fn is going to have to equal Fg. So we can say that the sum of the forces is equal to 0. And if up is positive, then we would say that Fn minus Fg equals 0. So these forces add up. to nothing. We could change the problem. We could make it slightly more interesting. We could lean on the book. Let's add something in here. Let's say someone leans on the book. So there's a downward push on the book. There's an applied force, I'll call it. How would the sum of the force expression change with that added? Again, assuming that the book is still at rest. If the book's at rest, the sum of the forces has to equal 0. So what's the equation going to look like for the sum of those forces? It's still going to equal 0, but what would the sum part look like? Yeah, the positive and negativeness is just a direction. So because FA and FG are acting down, and we have defined up to be positive, these two are going to be both negative in our sum, and Fn is still the only upward force here. And so this actually gives us an idea for how the normal force behaves. In this case, we could solve this thing for Fn. If I solved it for Fn, I would add these two to the other side, and we would get that the normal force would have to be the sum of the applied force and gravity. So the normal force is going to rise as you push harder and harder down on this thing, to the point where, and it will continue to rise until you compromise the structural integrity of the table, until you break the table. And at that point, this will drop to 0, and you will start accelerating rather quickly. So another example, if I drop a book from 2 meters, there is only a downwards gravitational force acting on it. Now that the forces on it are unbalanced, I mean, it's a simple, easy question. A dropped object is going to accelerate. You know this. We looked at this in kinematics. But now this chapter wants to talk about, well, why is that? We talked about the acceleration due to gravity, but now it's going to be more than that. We're going to start talking about, because the reason it's falling, the reason it's accelerating downwards is because there is gravity acting downwards on the thing. And rather than saying, well, the acceleration of gravity is equal to 9.81 meters per second squared, we can say it this way. We can say that Fg, well, if F net equals ma, which here they said, and we did talk about it a little bit on Thursday, that means that Fg is going to equal ma. And so the force of gravity is going to be equal to the mass times the acceleration. Or you could say, you could measure the force of gravity on the object. We could solve for the acceleration, for example. So now there's a reason for why the acceleration is what it is, as far as Newton was concerned. Einstein came along and completely undid it. And when we get to that, I'll show you guys a video on how gravity is not actually a force, completely kind of undo what we're about to do. But I'll save that for a later time. So a couple more examples here. We're talking about inertia. If you're riding a skateboard or a scooter or a unicycle, or like, again, people in the 90s were kind of dumb. My buddies would ride in shopping carts and push each other at curbs. Just, this is the kind of stuff we did before the internet. What happens? I mean, the skateboard's the easiest one to think about. Yeah, the skateboard comes to a stop, and because you're not attached to the skateboard, your inertia, and it's easier to stop the skateboard. You and the skateboard are not attached, even though you're standing on it. The skateboard has a much smaller mass. It's easy to bring to a stop. You're moving at the same speed, but you have a much higher mass than the skateboard does. So you have that much more inertia. You're going to go flying. And I've got a cool little drawing I did for this one before, so I'll draw it for you here too. There's the curb. Here's my fancy skateboard. Here's you. With some speed lines, because you keep going. or the turn on the car. We've talked about this too. While you're sitting in the back seat of a car, it makes a hard right turn. What happens to you? Well, let's draw it. Here's the car. Let's zoom this in because it's going to be a tiny drawing. And I'm going to put you in the back seat. The car does this. Who's ever driving turns the wheels, but you're not really attached to the car either. You are a distinct part. Yes, you're sitting on the seat. Yes, you might be wearing a seatbelt, but you're not like bolted to the frame. So your body has a desire to keep going this way. So when the car starts to make the turn, I'll go back to my blue. You want to keep going that way, which is why you get squished. You hit the side of the car. Because you want to keep going straight. You don't actually want to keep going straight. Your body wants to. Your inertia says, I was going straight, I'm going to maintain straightness. I don't know, I mean, field trips used to be a lot more common than they are these days, but I can think back to field trips riding the bus. Bus goes around a corner or a roundabout, and it was just an excuse to pin the guy who was ever on the outside of the car. You try and crush him in there. You get 3 to a seat in an elementary school bus, and you're just like crushing people against the windows. The most epic memory I had of something like that was we had a bus driver take us around a roundabout a couple times, and we were all cheering and crushing the people on the outside. Because again, the body wants to go straight, but the bus keeps making the turn. So that is why it feels like you're getting squished. Your body just wants to keep doing what it was doing, and the bus says no. That's why you get squished. Good times. And then the last one I've got here, headrests are placed in cars to prevent whiplash injuries during rear-end collisions. How is that possible? Hey, did Jan give you grief on today about
what?
You took one of my tests to James?
Oh, yeah, I totally messed that up on Thursday.
Because I was asking this, hey, is he here?
Yeah, he showed up. He hid in the library during your block, and as a result, he gets to sit with John and write his math test that he's behind on.
Nice. Give him some pack for me, too.
Sure. I bet he did really well on that test.
He or Jan?
Well, yeah, of course.
Okay, last one. Headrests are placed in cars to prevent whiplash injuries during rear-end collisions. How does that happen? So rear-end collisions are nasty things. Let's just draw a seat here. Draw a little chair. There's the chair in the car. And here's you. No headrest. Your head is above the thing. Here's you in the car. Yeah, it'd be bad, right? What's going to happen? And you're at a stop. So our gut tells us the head gets whipped back. But is that what actually happens here? The car moves forward. Because the seat, generally speaking, seats, and again, the more expensive the car, the more you'll experience this, but the seats are really supposed to be molded to you. In a school bus, the cheapest of all the seats you can buy, they're solid. But as you get more and more high-end vehicles, my first real car purchase was an Acura. I was so stoked. And I would sit in that thing, and the seat would be like kind of around me. I'm like, yes, this is what it should feel like. And the reason sorry? Yeah, but it felt like being in a jet. Or you go to the car show, and you sit in a high-end, like a luxury car, like it feels like sitting in a jet. Like it's just like, and when the car goes, you feel like you're a part of the car. And that is because these things are so capable of changing their velocity so quickly, your body needs to be as one with the car as humanly possible. In something like this, you get rear-ended, if you're at a stop, all of a sudden your body's going to lurch forward. Your head is just going to stay where the head was. Yes. So I'm going to say, there's a printer on the desk right there. Underneath it, there's a box, and in that box, there's going to be open paper. Take from there. When you get rear-ended, the head wants to stay where it is. Unfortunately, the rest of you wants to keep going forward. And now you have a problem. Without a headrest, this is what you're going to experience. It wasn't moving. It's because your head weighs a lot. You guys don't notice it because you were born with it. It grows up with you. But your head weighs about 20 pounds. That's not an insignificant mass. It doesn't just want to, and your neck's not very strong. You can break a human neck with about 4 pounds of pressure. Like if someone doesn't know you're coming up behind them and you apply about 4 pounds to the back of their neck, you can break a neck. It's not difficult to do. The reason that doesn't happen is because people generally, like, you're supporting your head, your muscles are tense. Someone pushes on your head, your body responds quickly, but it doesn't take much. And so you can get some pretty intense soft tissue injuries. You put a headrest here, and now all of a sudden, it catches you. It brings your head forward with you. It makes your head move with your body, and now all of a sudden you're not, experiencing that. Which is why headrests are so important. We don't think about them, but they really are. So that's it. This is Newton's first law, this idea that objects in motion stay in motion, objects at rest stay at rest unless acted upon by an outside force. There's about 15 minutes left in class. And what I'm going to get you to do is I want you to do this page here. The inertia worksheet 1. There's 7 questions there. And either on your own or feel free to discuss them with the people around you. I want you to try, and don't do 5. 5 has nothing to do with this. 5 will come later. We'll talk about the difference between mass and weight later. Don't worry about it. See if you can talk your way through how these are going to go. And we'll take them up. We'll discuss them tomorrow.